Because of course I would never make a thread. Okay. So what I want to do today is talk a little bit about optimization. I want to talk a little bit about how do you find maximum and minimum. So I want to start off with some results from Calc 1, and then move on to what changes in Calc 3. I'm not going to go over some of the things that are in the video. That's the whole point of watching the video. So, first derivative. So, f prime of a greater than 0. F is increasing to right and decreasing to the left. And if f prime of a is less than 0, it's the opposite. So in the video online, it goes through the derivation using the definition of the derivative of why this is true. If you think about this, let's say over here, here's the x-axis. Here's f prime. I really like plotting functions like this. This is a technique that's not really taught that much anymore because everybody uses computers. They weren't quite as prevalent when I was young. So here's A, here's f prime. Imagine f prime is positive near A. What this means is my function is increasing. F prime is my speed. So if I start here at A, a short time later, I had to have increased a little bit. A short time earlier, I had to have been a little bit closer to home. So by looking at the sign of the first derivative, I can get a really good sense of what my function is doing. If the first derivative is positive, I'm increasing. If the first derivative is negative, I'm decreasing. So if I want to find a maximum or minimum, could I have a maximum if the first derivative is positive? Okay, why not?
Because it's increasing, so it could only be at the boundaries.
Good. So if the first derivative is positive here, I just wait a little bit of time, and my function will be larger. And if I go back a little bit in time, my function would be smaller. So it can't be a maximum, can't be a minimum. So let's quantify this a little bit. So to find max min, what do we look for?
The critical points in the end.
Damn it. You're the first one in all these years who actually said that. And this is when we're being recorded. Fine. So in the interests of doctoring the video, can you give me a worse answer?
The critical.
Thank you. But of course, email me that you know. Look for critical points, i.e. places where f prime of x equals 0. Okay. So this is the first time in 15 years of teaching calculus that somebody actually remembered to say endpoints. So I will still go through the experiment that I did at 10 o'clock. We'll be doing the drowning swimmer later today, so this is going to serve double duty. Okay? I want you to tell me where my speed is largest walking along the room. Okay? Ready? If you want to try, by all means go, but it's going to... Ready?
Yep.
Okay. Where is the speed largest? Like, at where? At the endpoints, right? Most people forget about the endpoints. So when you're trying to figure out what's going on, here's A, here's B. Maybe my first derivative is always positive. And so you would say, well, this can't be a maximum or minimum because my first derivative is positive. Wait a little bit more time. The reason it can't be a maximum is because I'm not allowed to wait any more time. So if I'm trying to figure out where my function is largest, I have to check the endpoints separately. Because I could be at the point where I'm not allowed to go beyond B. And this is why I like to crash into the wall. This is the first time I've actually done it with a life jacket, which makes the lecture a lot more pleasant to do. Okay? So I try to do this to really drive home the point of checking the endpoints. This is one of the most forgotten things, is people just assume it's enough to find the critical points, check the critical points. These are candidates, but these are not the only candidates. And in fact, you could have a critical point that's not a maximum or minimum. So a great example is f of x equals x cubed. And so if you plot this function, it's going to look like this. So f prime of x is 3x squared, critical point is x equals 0. So here's a place where I have a critical point, but it's not a maximum, it's not a minimum. Does anybody remember any tests to determine when we have a maximum and minimum?
You can test if the slope is opposite on either side of...
Excellent. Do you remember what that's called?
No.
Okay. You guys are on fire today. And there's actually going to be a challenge on Friday against section 1. And I know this is being recorded. Right now, I would say the line is on section 2. Okay? You guys are the team to beat. It's called the first derivative test. And it basically says, you know, again, I like to draw it as here's x, here's f prime, here's my point A. Imagine the derivative is 0 at A, and it's negative beforehand and positive after. What this means is since it's negative, my function is decreasing down to A, and then it starts increasing. So it's got to be something that looks like this. So negative 0 positive means a minimum. Okay. What's the other thing I could have?
Second derivative test.
Okay, well, I mean, related to this.
Positive derivative.
Positive 0, negative. So positive 0, negative would be a maximum. So this is the first derivative test. Yes?
Why do you need a 0 in there? Because wouldn't it be still max or min if it was like...
So, by continuity, if I'm going to assume my first derivative is continuous, the value here has to be 0. This is a great question. Now, if the value here is not 0 and my function is discontinuous, then it becomes really interesting. How does a discontinuity in the first derivative affect the continuity of the function in the original function? So, for example, it's a great question. Let's imagine I give you something like this. So I'm decreasing, and then maybe somehow I bump up like this. Because something strange has happened at that point, where things have broken down. So I want to eliminate possibilities like that. And so if I assume my first derivative is continuous, then I will be safe. Yes?
Why can't there just be a change from positive to negative at a point that's not 0?
Well, basically by continuity, the intermediate value theorem. If my function is continuous, I can't go from negative values to positive values.
Oh, okay.
So, later in the semester, how many of you have seen the TV show Friends? Except for 1 or 2 episodes, what does every episode begin with? The title of every episode. The one with, right? When we get to the fundamental theorem of calculus, the lecture will be titled The One with the Mean Value Theorem. To me, the mean value theorem is one of the key results in Calc 1. It's amazing how many things you get from the mean value theorem. It's really Taylor series light. And the mean value theorem is an immediate consequence of the intermediate value theorem. That if you have a continuous function, you can't go from negative to positive values without passing through 0. Think of it as the transporters from Star Trek are not allowed. You have to move continuously. So that's why it's got to go through 0 if it's going from negative to positive. Okay. So several people have mentioned the second derivative test. Anybody remember the second derivative test?
Negative's a maximum, if it's positive, it's a minimum.
Excellent. So the second derivative test. So f prime of A equals 0, f double prime of A greater than 0. Is it a minimum or a maximum? Minimum. And if f double prime of A is less than 0, it is a maximum. I know this is being recorded, I probably shouldn't admit this, but I never remember the second derivative test. I always have to rederive it on the spot. I remember that something like the second derivative test exists. I just keep forgetting, is it positive, does that mean minimum or maximum? It turns out, if you can just remember that something like the second derivative test exists, you can actually rederive the second derivative test on the spot. all you have to do is check a really simple function. What would be a good function to check? What's a good function to check?
X squared.
Excellent. So I could do f of x equals x squared. I could do f of x equals negative x squared. So it's going to look like this. It's going to look like this. F prime of x equals 0. So the critical point is x equals 0. F prime of x is equal to negative 2x. So the critical point again is x equals 0. F double prime of x, however, oh, I'm sorry, f prime of x is 2x. Sorry. F double prime of x is 2. Here, f double prime of x is always negative 2. So if I remember that something like the second derivative test exists, this is enough for me to figure it out. Ah, my second derivative is positive. Looking at my parabola, this is a minimum. That's my second derivative. The following is almost surely a false story. It's almost surely an apocryphal story, but it's a funny story, and I like to imagine something like this actually happened. So the story is told about the construction of the stealth fighter and the stealth bomber. What is the objective if you're building a stealth fighter or a stealth bomber? Not to be detected, to maximize stealthiness. So the story is told about how people were trying to maximize stealthiness, and they searched for a critical point, and they didn't check to see were they a maximum or a minimum. And so technically it was the I'm here plane. Again, almost surely this is false, almost surely you're not going to have people, and now we'll just have this bright balloon coming, But I do see situations like this happening all the time. People forget to check conditions. Check and see, do you have a maximum or minimum? Here are two different ways to check. Now, a lot of times you actually don't have to do this. From physical grounds, you will know if you have a maximum or minimum. And so you won't have to worry about a lot of these issues. But in other situations, it's not going to be clear, do you have a maximum or minimum? So you should go through and you should check. Yes?
If you do the first and second derivative test and find a critical point and then do the second derivative test, is it definitely a maximum or minimum?
Yes. Now, as long as the second derivative is positive or negative. If the second derivative is 0, it's indeterminate. And so if you take the function f of x equals x cubed, which I gave you earlier, the second derivative there is 0. The second derivative test provides no information. Now, interestingly, in that case, the first derivative test does provide information. And so sometimes the first derivative test will work and the second derivative test will not work. The first derivative test is very powerful. Why might you prefer the second derivative test to the first derivative test?
It allows you to go faster as long as you can fail.
I'm sorry?
It allows you to go faster.
Right, you only have to figure out what's going on at one point. You just take another derivative. The first derivative test, you have to evaluate the sign of the first derivative on both sides. So the first derivative test is frequently a little bit more work. Okay? Any questions on what we've done up till now? So this is, the basics of, how we find candidates. We look for maximum, minima. We look for first and second derivative tests to figure out. Yes.
Should you always do the first and second derivative?
Nope. As long as one test works, as long as one test is definitive, you're done. And usually the second derivative test is easier to use. But sometimes the second derivative is very painful in trying to evaluate it. It could be so bad it's easier to just look at the sign. Because you don't have to figure out exactly what the values of the function are. You just have to figure out the sign of the values. Okay. How many of you have done the Farmer-Brown problem from calculus? Okay, what's Farmer-Brown's problem?
He's trying to make a fence to keep in his livestock, and he's got a certain length of fencing that he can make. And you're trying to determine how he can make it most cheaply.
Right. Not most cheaply. That's a different farmer.
With the greatest area?
With the greatest area. And Farmer Brown has an issue. What is the issue Farmer Brown has?
He's a limited number, he has a limited length
Nope.
of fence?
He only, yes.
He only uses straight lines.
He only uses more than just straight lines.
He only uses perfect squares.
Nope. Close.
He only uses rectangles.
Only uses rectangles. Farmer Brown loves rectangles. And he refuses to consider any shape that's not a rectangular pen. Out of curiosity, what do you think would be the best shape to use to enclose maximum area with a given perimeter?
A circle.
Circle. And so if you have to do a rectangle, which rectangle do you think will be the best?
Square.
Square. So we're going to see how to do this as a Calc 1 problem. It's really a Calc 3 problem. My son was helping me prepare this lecture. I'm going to try to show him a way to do this without using calculus. Little story time. How many of you have read the book Click Clack Moo, Cows That Type? There's a whole series of these books. These are really good. I will read the beginning because after the beginning it starts getting bad. Farmer Brown has a problem. Now unfortunately they don't feel that little kids can understand calculus, and so rather than having him have his cows that have to be put in a pen, they change it to his cows like to type. All day long he hears click clack moo, click clack moo, click clack moo. Okay. I do believe though that you can actually do calculus with 6 and 7-year-olds, and so I will let you know how it goes tonight with Cameron. He's very excited about staying up late to do the Farmer Brown problem the way it should be done. Okay? Farmer Brown. Only rectangles. 40 meters of fence. Maximize area. So whenever you have a problem like this, anybody know what step 1 is in problems like this? What's the first thing you should do?
Try relating all the variables to each other.
Before you even relate the variables.
Draw a picture.
Draw a picture. Doesn't have to be a good picture. If you want to draw cows as well, that's fine. You just need some kind of picture. So let's call the sides x, x, y, and y. And so we're given, what constraint are we given? 40 meters of fence. So how would we write that?
2x plus 2y.
So one way is we could write it as 2x plus 2y equals 40. I prefer to do a slightly different given. What given do you think I prefer? Yeah, x plus y equals 20. I prefer to use the semi-perimeter rather than the perimeter. And the goal, and it's nice to write down what your goal, what you're trying to do, is maximize x times y. So this is a function of 2 variables. Fortunately, we're learning how to deal with functions of 2 variables in this class. We're learning how to maximize, we're going to learn how to maximize and minimize things like this. Okay? And so when I have something like this, I have something that's legitimately a function of 2 variables. And the question is, can I develop a technique of 2 variables to handle this? Well, let's go back to what we did in 1 dimension. In 1 dimension, how many possible endpoints can you have? Yes. You could have 2. What else could you have? I could have 2 endpoints. I could have like interval 5, 6. I could have 2 endpoints. What else could I have? 1 endpoint. I could have the interval 5 to infinity. What else could I have? 0 endpoints. I could have the whole real line. So at worst case, when you're doing Calc 1, there's 2 endpoints to check, worst case. That's not so bad. In Calc 3, however, you have some region, and now the endpoints become the boundary. And unfortunately now the boundary could become infinitely many points. And so in fact over here, I have infinitely many points that are on the boundary that I have to check. Things become even worse as the dimension gets higher and higher and higher. This is why Calc 3 is significantly harder. Now fortunately, we can bypass Calc 3 and solve this as a Calc 1 problem. We can solve for x in terms of y or y in terms of x, and reduce this to a function of 1 variable. Which should we solve for x or for y? Doesn't matter, but what should we do it for? X. Most people would solve for y in terms of x. And people are just more familiar with, I have a function of x rather than I have a function of y. It doesn't matter. You can do it either way. It's just a familiarity with the algebra. The amount of calculus we do is going to be minimal. So, since y equals 20 minus x, we want to maximize the function a of x is x times 20 minus x. Or, we want to maximize the function a of x. Who's our favorite New England transcendentalist? Thoreau. 20x minus x squared. I think it's nice to just write it out and then avoid using the product rule. So look for critical points. and look for endpoints. So what is the range of x that I have to consider for this problem? What are the possible values for x?
0 to infinity. No, 0.
0 to infinity is fine, but we can do a little bit better than 0 to infinity. Yes?
0 to 20.
0 to 20. So the simplest thing is to say x can't be negative, so it's at least 0, and x can't be more than 40, because I only have 40 meters of fence. But x is counted twice. So it's subject to 0 less than equal to x less than equal to 20. I'm not going to go through this, but it's very important that I'm including the less than or equal to and not just saying less than. Do you think Farmer Brown is going to use 0 for the value of x? No, it'll give him 0 area. Simply, he's not going to use 20. We know the maximum or the maximum is not going to occur at the endpoints. But it's technically convenient to study this. And the reason is there's a big theorem that says if you have a continuous function on a closed bounded set, it attains its maximum and minimum somewhere. So what this means is if you're searching for the optimal value, it exists to be found. You may not be able to find it, but at least the subject of your searching exists. What class do you think you proved this in? This is one of the few times this year linear algebra only works 90% of the time. This is one of the few times all year where the answer is not linear algebra. It's real analysis. So if you continue with the math major, when you get to a class like real analysis, they will prove this theorem that a continuous function on a closed bounded set attains its maximum and minimum. So in my notes in the video, I go through what happens if you remove some of these conditions. What if the function is not continuous? What if the interval is not bounded? What if the interval is not closed? What if you don't have an endpoint? So I go through all those different cases in the notes so that if you remove any of those conditions, you have problems. So I'll try to hold this up just for 1 second. You can hit freeze on your YouTube. There you go. Yes?
Doesn't the function like y equals 0, though, not like
I'm sorry?
reach a maximum or minimum? Like what if you use the function like y equals 0?
Then every point is a maximum and minimum. So it does attain its maximum and minimum. It attains it everywhere. So here, we have to check the endpoints, and we have to check the critical points. So endpoints. Well, endpoints is not so bad. We get a of 0 is a of 20 is 0. And now the critical points, a prime of x equals 0 means 20x, I'm sorry, means a prime of x equals 20 minus 2x equals 0. That implies x equals 10. And so now we just have to test and see which one works. Is it the endpoint? Is it the critical point? How can I tell if this is a maximum or minimum? I could do second derivative. Second derivative would be really nice. I would just get -2. I could do the first derivative test. But I claim that it should be intuitively obvious in this problem that I'm going to have a maximum. Okay, this is the Farmer-Brown problem. Any questions about Farmer-Brown? Okay, and again, if Farmer-Brown was not wedded to rectangles, he would use a circle. Yes?
Just kind of one thing I missed.
Yep.
You mentioned that because we're account for infinite endpoints,
Right.
what did we do in this problem to deal with those endpoints? Or
What we did is we took the constraint x plus y equals 20, and we solved for y in terms of x. And so we got down to one function of one variable. So in the online video for today's lecture, I go through the box problem very slowly. And there we have 3 variables. We have a constraint that brings us down to 2 variables. We can't do better than that. It's fundamentally a multi-dimensional problem. Here, there is a trick I can do, and I can reduce it to being a one-dimensional problem.
But you can't always do that.
You can't always do that. This is special. As long as we're doing special things, I'll show you another trick you can do for some of these problems. It involves, in my mind, one of the least popular superheroes. So anybody know who Farmer Brown's cousin is? Or brother? We'll do his brother.
Farmer Bob.
Farmer Bob, exactly. So Farmer Bob also loves I'm using the word also, so it should be clear.
Rectangle.
Rectangles. So, only rectangles, but farm is along a straight river. And so the advantage that Farmer Bob has is he only has to do 3 sides of fencing. So Farmer Bob, it's going to be something like this: y, y, x. And now you have x plus 2y equals 40, and you want to maximize x times y. Any thoughts on what the answer should be? Yes?
2 squares next to each other.
What do you mean by 2 squares?
Like the area should be.
You need to tell me what x and y.
40 divided by 3.
So so all the sides are the same?
Yes, all the
Okay,
sides are
so make a square where all the sides are 40 divided by 3. That's the most natural thing to guess. It turns out that's wrong. So, yes.
It's 2, or x equals 2y.
So it turns out x equals 2y. So the best way I know to prove this is, well, one way, of course, is we could just do the calculus and the algebra. And if you do that, you will get the answer. I want to show you a way to get the answer by symmetry. Okay? These are very hard concepts to figure out how to bypass the calculation. So I think one of the least popular superheroes is Aquaman. Right? In all the revival of Marvel and DC, I don't recall seeing Aquaman anywhere. You know, I've seen him in old TV shows where he can throw balls of water under the sea. He can talk to the fish. He doesn't seem to be that popular. But today, in multivariable calculus, Aquaman is going to save the day. So remember how I said that this is bordering a river? Aquaman is going to make a pen for his fish at the exact same time as Farmer Bob, who may be Aquaman's secret identity, is making a pen for cows. And Aquaman also loves rectangles, which is why people believe he might actually be. So imagine Aquaman makes his pen at the same time as Farmer Bob makes his pen. Whatever is best for Farmer Bob is going to be best for Aquaman. And now if you look at this whole system, you have 80 meters of fence. If you have 80 meters of fence, what's the best thing you can do? Square. So Aquaman makes a rectangular pen, same dimensions as Bob, therefore it's a square of side 20. Right? It's beautiful symmetry that you don't have to do the calculations. You can get the answer just by looking at 2 problems, piecing them together, and seeing it's a problem you've already solved. Okay? This is math at its best. So later in the semester, on a homework problem, I might give you a problem where I ask you to minimize your distance to a point. What is problematic about working with distances? What's bad about working with distances? Square roots. Right? Square roots are not pleasant. We will see an example of square roots later today. What can I do to get rid of square roots? Square it. So if I ask you how much money you have in the bank, can you just square the money you have in the bank?
Wish.
Yeah, it would be wonderful if you could do that. You can't do that. But if I want to compare and say, figure out who has the most money, if instead of looking at how much money we have, if I look at the square of how much money we have, is that okay? Yeah. So rather than looking at distances, I can look at distance squared. The amount of calculus we do is minimal. Most of what we're going to be doing is algebra. And so it's all about trying to find the best way through the algebra. Okay? So this is a quick review of optimization in one dimension. And what we're really doing is revisiting some of the problems you've seen before and seeing that fundamentally they are a two-dimensional problem. And we will now start to develop the techniques to handle problems in several variables. So So there's two steps in terms of optimizing in several variables. So two steps to finding max and min in several variables. So step one, find the critical points. And step two is check the boundary points. So the only difference between this and what you've done in Calc 1 is that rather than using the word endpoints, I'm using the word boundary points. Sometimes in Calc 1 you say boundary points as well, so it's really not a big difference. The real question is, what is the notion of a critical point in several variables? So in one variable, it's, I want df dx, I want f prime of x to be 0. What do you think the critical point should be in several variables?
It's called the partial derivatives with respect to a single variable.
Excellent. So critical point means df at a equals rad f at a equals rad f at a. All these are equivalent notations. df dx1 at a dot 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 df dxn at a equals the 0 vector. And again, it's very important it's the 0 vector. What I'm saying is each component, each of these special derivatives vanish. That's what it means to be a critical point. Does this seem a natural generalization of a critical point from one dimension? Yeah, critical point in one dimension is, the derivative is equal to 0. Here, I'm defining my derivative as this vector, so rather than having the vector be the number 0, it has to be the vector 0. So now, it turns out that the only candidates for the interior critical points are the places where, the interior, maximum and minimum, are the places where the critical points happen. So I want to just justify why step 1 is true. So why step 1? So imagine I give you some set like this, and you take some point, and I'm searching to see if I have a maximum or minimum. And I say there's two things to check. Look at the places where the critical points are 0, and look at the points in the boundary. Alright, so right now I'm basically being extremely lazy, and I'm not saying anything about how to do anything meaningful on the boundary. I'm saying keep every point on the boundary under consideration. We need to somehow prune that. Otherwise we have infinitely many points to check and we will make no progress. So for now we're going to give up on checking the boundary. I claim that in the interior, however, I only need to look for places where the critical point is 0. Where the critical point happens, where the first derivative is 0. Those are going to be the only possible candidates for maximum and minimum. Well, let's think why this is true. Imagine I'm not at a critical point. Imagine the gradient, imagine the derivative is not 0. So if it's not 0, at least one component has to be non-zero. Which component would you like to assume is non-zero? Doesn't matter, any answer's fine. Which component do you want to assume is not 0? Yes?
X.
Okay,
X.
the first one. So we'll assume the first component is not 0. Do you want it to be positive or negative? Positive. So if I'm at a place where I'm not a critical point, at least one of my directions has a derivative that's not 0. Let's say it's in the first direction, along the x1 axis. It's positive, so if I move a little bit to the right, my function's increased. If I move a little bit to the left, my function's decreased. I can't be at a maximum. I can't be at a minimum. This is where we use the concept of open sets, which I mentioned just very briefly earlier, how you make calculus rigorous. And if I'm at an interior point, I have a small amount of movement I can do before I hit the boundary. So if the first derivative was positive in this direction, it can't be a maximum, it can't be a minimum. What if the first derivative was negative? Same argument, except you just flip, and now the function is decreasing to the right, increasing to the left. So if the first component is non-zero, it can't be a maximum. Then you just go component by component. What if the second component was not zero? Well, if it's positive, I'm increasing this way, I'm decreasing that way. And again, I can't be at a maximum or minimum. And the reason is, if I'm in the interior, I can always do a little bit of motion. I'm not hitting the wall. So this tells you that the candidates are going to be the places where the first derivative vanishes. Do you think that just because the first derivative vanishes, it will be a maximum or minimum? No. We've seen in Calc 1, the function x cubed has the first derivative vanish, but it's not a maximum or minimum at 0. Things like that continue, and you have saddle points. So you need a second derivative test. The second derivative test is a nightmare. What class would make the second derivative test more pleasant? You won't be burned. Linear algebra, okay? We're not going to have 2 classes in a row that are the correct answers that are not linear algebra. Right? Linear algebra gives you a much better way of understanding what's going on. You have a matrix formulation for the derivative. You have a way of re-expressing what's going on to very clearly see what's happening. I don't like talking about the second derivative test in Calc 3 without linear algebra. It's some unpleasant formulas to remember. But if you continue in math, revisit this subject after taking linear algebra. Okay. Any questions on what we've done so far? Alright, so it's time to do some examples. This is one of the few times where I prefer teaching at 10 o'clock rather than 11 o'clock because I deliberately did not look at the examples so I could look at the algebra from a fresh point of view. Sadly, my memory may be failing, but it's good enough that I can remember what I did 50 minutes ago. Okay, so let's take as an example f of xy equals x squared plus y squared minus 6x plus 3y, plus 2y plus 5. And we want to find the critical points. Alright, so we find df dx is going to be 2x minus 6. df dy is going to be 2y plus 2. So critical point means df dx, df dy equals 0, 0. So I need 2x minus 6 to be 0. I need 2y plus 2 to be 0. Once I've gone past this line, I'm done with my calculus. From this point onward, it's just algebra. Now, fortunately, this problem is rigged, so the algebra is pretty pleasant. Right? If 2x minus 6 equals 0, okay, a little bit of work, x equals 3. If 2y plus 2 equals 0, a little bit of work, y equals negative 1. Okay? That's it. So this is how you would find the critical points. Right. Let's do an example now where the algebra is a little bit meatier. So example, f of xy is going to be, I think it's x squared y plus 3xy squared. Alright. So I want to find the critical points. What's step 1? Yeah, find the partial derivatives. So find critical points. So df dx is going to be 2xy plus 6xy. df dy is going to be x squared plus 6xy. It looks like I made a mistake.
Wouldn't that be
Yeah,
3y
Yes.
squared? The other side, that one.
This one would be 3y squared. Thank you. And that's it for calculus. We're now back to algebra 1, algebra 2. So I have 2 equations and 2 unknowns. So we have to solve 2xy plus 3y squared equals 0 and x squared plus 6xy equals 0. So I have to simultaneously solve these two equations. So there's lots of ways to do this. Can somebody give me one way to start? Yes.
You could multiply the left one by 3.
That's my favorite way to do it. Is I could multiply this by 3 and you get 6xy plus 9y squared equals 0. I then substitute into here, 6xy is negative 9y squared. So 6xy is negative 9y squared. This gives me x squared minus 9y squared equals 0. What else could I do if I didn't see multiplying this by 3? What else could you do to try to solve two equations, two unknowns?
Well, I don't know if you can multiply it by negative 3 and add them. Like
So I can multiply by negative 3 now. That's essentially the same as this.
You can solve for xy.
I could solve for xy. Very similar to this. What else could I do?
Solve for x.
I could solve for x, and I could also
Solve for y.
I can solve for y. So here I can solve for x easily. Here I can solve for y easily. I think the easiest thing to do here is to do something like this. The danger in solving for x is you'd say 2xy is negative 3y squared. X is equal to negative 3/2 y. What's the danger?
You're eliminating the possibility that y is 0.
I'm eliminating the possibility that y equals 0. So if I just try to solve like that, there's the danger that maybe y was 0. So I'd have to put a little asterisk and note, consider separately the case y equals 0. So that's the danger when you divide. Whenever you divide, always make sure your denominator is not 0. Alright, so now we would get x equals plus or minus 3y from x squared minus 9y squared equals 0. Okay. Does that mean I have infinitely many critical points? Are all of these critical points? Or is there more work that needs to be done? Yes?
Can you just substitute that back into one of the two equations?
Yeah, I need to make sure that it satisfies both equations. Right? It's not enough to just get x equals plus or minus 3y. I now have to make sure it satisfies my two initial equations. So I have two cases, x equals plus 3y, x equals minus 3y. In the interest of time, I'll only do one case. Case 1, x equals 3y, we need to check. So now we have, in this equation, we'll get 6y squared plus 9y squared equals 0. And over here, we'll get 9y squared plus 18y squared equals 0. What's the only solution to those equations? Yes.
Y equals 0.
So only solution is y equals 0, which then implies x equals 0, because x is equal to 3y. Alright, that's case 1. Case 2, I'm not going to bother doing it, is just now x equals negative 3y, and you argue very simply. Okay. So, the algebra can get a little bit more involved. One advantage you have is if I'm giving you a problem on an exam or a homework, what do you know about the algebra?
Doable.
It's doable, right? That's the big difference between this class and real life. Now, there could be many different ways of doing the algebra. I suggest sometimes you have 3 or 4 different pieces of paper and start trying one of the approaches. And if it's not working, put the paper to the side, try another approach. If that doesn't work, try another approach. If you run out of approaches, go back and revisit one of the things you tried before and see if you can do better. Okay. Any questions on what we've done so far? All right. What I want to do now for the last 5 minutes of the class, okay. What I want to do for the last few minutes of the class is go back to the drowning swimmer problem. Another Calc 1 optimization has nice applications in physics. How many of you have seen or heard of the drowning swimmer? Alright, so we will pretend I'm tired. I stayed up late last night preparing this lecture. I'm no longer wearing my life jacket, and I'm drowning in the water. You are the lifeguard, and you're going to try to save me. Okay? You can't bear the fact that you might not have any more calculations. Okay? What is your goal as the lifeguard?
Get there as quickly as possible.
Get there as quickly as possible, right? Your goal is to save me. I'm trusting you to get there, okay? Now, I'm trusting you also to use calculus. Is it possible that the path you take would be the following?
If you're dizzy.
If you were dizzy, or maybe if you were over 21 and were out late drinking the previous night, but I believe everybody in this class is under 21, so we're not going to have any issues like that. You will not be taking curvy lines like that. You will take a straight line to me. What are the possible straight lines you could take to me? Yes?
You could do just the straight line between the 2 points.
I could just do the straight line between the 2 points. And in practice, this is what most lifeguards do. But do you run faster on land or swim faster in the water? On land. So one possibility is maybe you want to maximize how much time you spend on land. And so maybe you take a path like this. What do you think the worst thing to do would be? Straight up. Let me minimize the, this is where you're basically trying to, oh no, I really am trying to save my professor. But not really seriously. Okay? You go straight up like this and like this, I know you're putting on a show. What else could we do? This is 3 possibilities. What else could we do?
You want to play the currents?
Okay, so we're going to assume, just keep it simple, that there's no currents right now. I will also assume that there's either nobody on the beach, or the people on the beach will immediately get out of your way as they see you with your surfboard. So you don't have to worry about running into people. What else could we do?
Use a function and minimize, take the 2 velocities that you have in each, land and water, and then you'd add them and then try and minimize the distance. You'd have
Good, but you got to tell me what path I could take.
But
you're on the right track.
That depends on. Well, if you had a function that had I don't know, velocity times time.
No, we'll get to this, but you have to tell me what path. Physically describe the path.
Okay, well, you do part land, part water, but that's the amount of each is determined by the optimization of the function.
Okay, so you give me some point here. I run like this, and I come in like that. And then you're telling me the procedure to how to figure out where to go. You want to minimize this time plus this prime. Yeah. And in physics, if you talk about light traveling between 2 different media with different refractive indices, n1 and 2, light takes the path of least time. Light moves at different speeds in the different media. And so when you do a problem like this, you can always normalize some of the lengths. I can assume that this length is 1 unit. And I can assume my speed on the land is 1 unit. I can adjust my time like that. I'll have this distance here be A, this distance here be B, and I'll have this as some point X, and I'll have some speed V water. One of my favorite things is, I know a little bit about how my answer must depend on V land and V water. The answer should only be a function of the ratio of V land and V water. Because I can always adjust my time units to make my speed on land 1 unit. So whatever the answer is, I have some idea of the functional form of the answer before doing any of the calculations. So how long do I spend on land? Time on land, as a function of x, is the distance on land. Well look, what kind of triangle is this? It's a right triangle. So the hypotenuse is the square root of a squared plus x squared, and then I divide by v land, and that's my time on land. And this was what was suggested a moment ago. My time in the water is going to be the square root of v squared plus 1 minus x squared divided by v water. And now I want to minimize the time, which will be t land of x plus t water of x. What's interesting is, because of the square roots, this is a somewhat painful function to work with. I recommend you try to do the algebra. If you do that, you're actually going to have to solve a quadric. a degree 4 polynomial. How many lifeguards do you think solve degree 4 polynomials when they see someone drowning? No one who comes back. How many lifeguards do you think have tables of where to run based on where they're standing and someone is drowning? They see somebody drowning and they go to their lookup table to see where to run. For all practical purposes, this is a pretty good path. It's not that far off. Which way do you think you would want to err? Going a little bit towards the left or a little bit towards the right? Probably towards the right. Spend a little bit more time on land where you're faster and a little bit less time in water where you're slower. And then as was suggested, we can consider twists in the problem where we now start putting in currents. And depending on how the currents are going and which way you're going, that can make a lot of interesting features. Alright, so this is a really good, quick introduction to optimization. There's more examples in the videos online. Friday's class is going to be on the method of least squares. If you haven't watched the video, that's wrong, but this is the one time all semester where it will be okay not to watch the video. Okay. Then the advanced lunch will be today right now.